record on this computer. All right, so the first investigation was talking about sorting and comparing. So it gives a definition of sorting, but we're leaving it to young children. The verbiage of young children, because the curricula, and really this is not just limited to New York State. It's all across the country, the world, and everything. It's an ever evolving thing, to the massive amounts of frustration of all teachers everywhere. So what happens is every few years, like a weather pattern, or just like a recession, education takes a turn, and people decide, okay, we're going to scrap the old system and we're going to roll out a new system. It seems to coincide with presidential administrations, but and when they do that, it's from the top down, and they say, we're changing everything. We're going to have all of our kids be the best and the brightest in the world because we're the best and the brightest, and that's how it's going to be. And then they tell all the educators, you're going to change the whole thing. This is the stuff that we need you to teach. And then we look at the list of the things that they want us to teach, and it's exactly the same, just in maybe a slightly different order, right? So we say young children here because, while this is an activity that's typically for a preschool child, or a kindergartner, for all we know, in 5 years, it could be something for a toddler. And actually it would apply for even toddlers. There's no reason you can't start this off even younger. But later on, I do get a little bit more specific, right? So sorting means taking a group of objects that are given and putting them into groups based on some characteristic like color, shape, size, blah, blah, blah. Comparing means looking at two objects and using a comparison word. That's the key component there, like bigger, more, heavier, taller, higher, etc., to describe the relationship between the objects or sets. All right, when I assign this, and when I assign every investigation, it's always with the thought in mind that if you do it, you're getting full credit, right? Whether you gain something from the process is a different story, because that's entirely up to you, right? So, as I was looking over it, I saw varying degrees of quality. It was clear that some folks, whatever the deadline was, 5 minutes before that is when it was done. And then there were some people that, really, really got into it and took a deep and focused look at the idea and really tried to dive into what was going on, right? So the assignment, give two examples of sorting that a preschool child might do, one from life outside of school and one in a school setting. Be as specific as you can. So you can go about this a couple of different ways. One way would be to say, oh, and this is the answer, number one. One way would be to say, all right, sorting. What can a kid do? They can sort crayons. They can sort pencils by color, colored pencils by color, crayons by color. They can sort socks. We always have to sort our socks. Things like that. Or you can start thinking about something very specific. And I don't need an essay. I don't need a narrative, but something that has a little bit more depth, and maybe if you're looking for something that might apply to an entire group, something that everybody can relate to, right? So I saw a lot of examples involving crayons. Crayons are good because most kids at that age level are going to be familiar with crayons, right? So an example, a very popular example I saw that was a solid example, and let me get rid of this and clean it up a little bit. Sort crayons by color. All right, two examples. Yeah, now sorting crayons by color, that could happen in school or out of school. All right, so you just decide which one you want this to be, and then you have to think of another example, right? So we'll designate it in a second, but another example, let's say that we're looking at, again, something that would apply to the entire population of students, right? So you go down the list and maybe you brainstorm some ideas, right? So what would be some things that everybody is familiar with, right? Because I teach a stat class and I start talking about games of chance, rolling dice, selecting cards from a deck. And when I first taught that stat class, I operated under the assumption that everybody knew how many cards were in the deck and what kind of cards were in the deck. And it was like a 50-50 split, where it's like, okay, I know there's like some red and some black ones in there, but that's all I know. Maybe like there's a Queen of Hearts because there's a song about that, you know. But aside from that, it was kind of hit or miss. So you kind of want to stay away from things that might be too of the niche category. Also, we just talked about color. So maybe we want to sort something else, right? So we can sort, I saw this one, this is a very nice example. Sort recycling based off of type, you know, so based on type. Oh, poor quality watch, geez, shook, crazy like, right? So sort recycling based on type. Now this could actually happen in both places also, in school and out of school. So you can go either way. So I'm just gonna call it and say that this one is the home and this one is the school, but it could very well be the other way around. You know, as my son came home from preschool and he was gung ho about recycling. They had him doing it at school. You know, he's like, he saw me throwing the boxes and the water bottles into the same bin. He's like, what are you doing? He didn't say it like that, but you know, he said it in like kid talk. What are you doing, Daddy? And I was like, oh no, don't worry about it, bud. I put it all together and then I pull it apart later on, you know, because I live in a 2-bedroom condo, so there's only so much room, you know. So it is possible that these examples can go either way. Now, in the case of number 2, we're doing a comparison, so bigger, smaller, and stuff like that. Now, this is something that you may not necessarily consider if you're just kind of getting started on this journey. If you have any experience with early childhood development, then you know that maybe having kids compare things like their height could be a tricky subject, right? So, you know, depending on the age group. Some, you know, there are certain age groups where they're just oblivious to anything. Everybody's their friend. But then they get into a certain mindset where, you know, like, wait, I'm the shortest one here. Now we got an activity where we have to compare heights. All right, who's the tallest? Billy. Who's the shortest? Well, me, because I'm the shortest. And now I really feel like the shortest one. Right? They don't say that. They just start hysterically crying. Right? So you probably want to stay away from things that talk about physical characteristics. Right? So you can get into sorting, and there's nothing wrong with size. You know, you could talk about a milk cartons, for example. So compare milk carton sizes. All right, that could happen at home or in school, but I'd venture to say that's more probably a home thing. You know, like you have a quart of milk versus a gallon, not a gallon, that wouldn't be in a carton, but like a half gallon versus a quart versus a pint. So I'll make a note of that just in case it's not something obvious to you. So quart, I'll start with the smallest actually, pint, quart, half gallon. And something you could do at school that's kind of like along the lines of just being just generally safe. I mean, you can compare size. That you go back to the crayons, compare the size of each crayon. Used though. All right, so because if you ever want to make a preschooler frustrated, ask them which is bigger and then give them two things that are exactly the same size. Because at that age level, there is very little gray area. Right? There's not the ability to establish causal relationships has not developed in their brains. So they're at a point where everything is either this or that. And so you start looking at logic based arguments. And so, like maybe you remember some discussions of logic in a math class. The first thing you talk about is the and relationship, this and that. Then you talk about or, and or is very confusing to a young child because if I tell you you could have either the pink lemonade or the cranberry juice, it's a choice. But mathematically, or allows for both possible outcomes, right? So that allows for some confusion. But then when you get into conditionals, that's where everything starts falling apart, right? They have a lot of difficulty understanding what happens if the premise is not met. So if I were to say something like, if it rains, then we will not go outside, right? So we're talking about recess. If it rains, then we will not go outside. So it didn't rain, okay? It didn't rain at all. And recess did not go outside. It stayed inside. We did an inside activity. The kids are like straight up flipping out, all right? But you didn't lie to them because you never told them what would happen if it didn't rain. You just told them what would happen if it did rain, what the consequence would be if it did rain. They just assumed that if it didn't rain, that the opposite would be true, that you would just go outside, right? They can't wrap their brains around at that early age. They can't wrap their brains around the fact that there are other possible outcomes that could be at play, right? So you got to be very explicit with your instructions when it comes to activities, assignments, tasks, simple phrases that get the job done. And I'll even say all the way up through middle school, simple phrases will get the best possible outcomes in terms of directions. When you start having convoluted instructions for whatever the task is, then that's when things start falling apart. Now, if your objective is for them to critically evaluate a set of instructions to understand what the instructions are asking, then it's a different story. Make it as convoluted as you want. But generally, you want to keep it as simple as possible, right? So, this is bare bones. I didn't really elaborate on much of anything, but yeah, you got to start getting to a point if you're gonna do this for real as a career. You don't want to think, all right, compare milk carton sizes. All right, well that sounds great. If you ask kids to go home and compare milk carton sizes, you better be pretty sure that they all have milk cartons to compare in terms of size, right? So, and then you got to be very specific about what you're asking them to compare about those milk cartons, right? Because they'll come in the next day and say one was blue and the other was green, and so you got to be specific about what it is that you're asking them to do. Right? So that was the first investigation. And again, as long as you did it, you got full credit. That one, I'm pretty sure, yeah, I definitely scored some of them. I just haven't gotten to everything. Tomorrow's going to be my big day. Where on earth? There's 3. I don't know where 3 went. All right, let me try bringing it in again.
So do we email them to you, or do you just want us to tell you we did them?
Oh, no. There's you submit them on Blackboard.
Okay. Let me see.
All right, so then we have number 3, because we skipped number 2. So number 3, table is set for lunch, but there are no napkins at the places. Okay, so where they're going to sit. The young child is given a package of napkins and asked to provide every place with a napkin. The child grabs a bunch of napkins from the package and starts to do the task. Explain how the child can eventually be successful even if he or she does not yet know how to count. All right? So the short answer, and so we don't spend all night going over these, but the short answer is they would distribute evenly the napkins. All right. So what they want to do, again, they want to give every place a napkin. So it's like dealing from a deck of cards, but that's an analogy that only adults or these kids who have experience with cards would understand. So if you're assuming that the child has no experience with really anything along these lines, the child, as long as they know that they need to match one napkin with one place setting, then move on to the second place setting. And repeat until until all settings have a napkin. What you have, so you start off at one location. You tell them you just start somewhere. You got to match. You got all these napkins. You're gonna match one napkin with one place setting. All right. So you got a place setting there. You got a napkin. So take a napkin and match it with a place setting. Let them decide, and then match another napkin with another place setting. And so they don't know how to count. They don't have to go around and say that there's 12 place settings that I have to account for, and I got to count out 12 napkins to make this happen. They are going to distribute the napkins to each setting. So what they're actually doing here, in a very commonplace sort of way, is they're learning distributive property. It's actually these formative cases, examples, that allow us to reflect back on those later on when we're talking about, like in an algebra class, when you actually deal with that thing called the distributive property. We actually refer back to these kind of examples and say, all right, so what are we doing when we're distributing a 2 to each term in the binomial? What we're doing is we're pretending that we're a dealer dealing a deck of cards. We're a kid setting the table for dinner. They're like, everybody's going to get a fork. Everybody's going to get a knife. Everybody's going to get a napkin. Everybody's going to get a plate, and so on. So we're actually developing the basis or the foundation to understand the more complicated stuff down the line, right? But this is not, and this is very important to understand, this is not a summative task. It's not something that you're asking them to do for a grade. I mean, it's generally, we're talking about preschool and kindergarten and stuff like that, but you would never ask a kid to set the table for lunch and then tell them that they're going to get a 100 on the test for it. You might give them a little treat. That's a different story. But generally, if you're teaching responsibility along the same lines, everybody's got a chore, everybody's got a job. Oh, we're getting ready for lunch. Okay, so Charlie, you're gonna pick up the toys. Murphy, you're gonna set the table by putting out the juice boxes, and everybody gets a little something else to do. All right, so that's all part of the fun, but it's also teaching them these mathematical principles along the way. Right, and so the only this is my favorite line in this course, and it's a powerful line, but it's also something that it's so hard to really kind of like make happen. I'll say it. The only job of an elementary school teacher when they're actually teaching the mathematics is not to ruin the foundation that was built with all of these little tasks that have been taking place over the course of years. So when that kid gets into a 3rd or 4th grade class, the teacher has it within their power to either build upon all those formative years or totally destroy everything that they've already learned up until that moment. And the way they can do that is by not connecting the current material to the stuff that they already know. All right. So, and how do you do that? You just keep giving them worksheets. You give them unrelatable practice problems. If you can make it, and I've said this before, if you can make it a game or make it a story, even it's hard to think that this could happen, but even in a math class, there's no reason why you can't make it entertaining, make it a story. And I'm not talking about like, imagine your favorite math teacher and like, what did you like about them? The fact that they went on a half an hour tangent talking about their new puppy, like I'm not talking about that kind of entertaining. I'm talking about the way that you can entertain while also teaching the content. It's a very tricky concept, especially for math. For history, like it's easy because it's all a story. English, you're literally reading stories. So it's just a matter of whether or not you enjoy those stories. But here, you got to kind of force the issue. You got to make it connectable and relatable. Right. Number 2, a child is given a set of blue counters and a set of red counters. The child also does not yet know how to count, but is asked to tell whether there are more red ones or more blue ones. How can she or he do it? Right. So oftentimes we want to dictate the learning. We want to say, do it like this, do it like that. Follow these steps and it'll all work out in the end, I promise. But sometimes you just want to let them go do it and see where it takes them. All right. And, the issue that we run into as learners get older is it has nothing to do with intelligence. It has nothing to do with the ability or the patience of the teacher. It has everything to do with time. Okay. And the fact that there just simply is not enough time to let everybody just explore on their own, make all the mistakes that they want, and discover the concept without having guidance or direct guidance. Right. So that's why in math classes, more than any other class, it's here's the rule. Now that you have the rule, let's practice applying it. The fundamental concepts underlying that rule is like, it could be pretty important. It could be the key to understanding everything that follows, but you never got that foundational that foundational message, right? So in this case, you have somebody that needs to just look at something and determine what's more and what's less, right? So you let them do it, but if you put your mind or yourself in the mind of a child, what are they going to do? They're probably going to make piles. Of red and blues and compare the size. All right. I always, well, I often joke that, sometimes the answer to a math question is x equals 27. And then sometimes the answer to a math question is a lot. And there is merit to that. Because if somebody said, how much does that house cost? And the answer was more money than you'll ever make. Hey, they gave you the answer you need to know. Do you need to know the precise value? You can't afford it. You know that it's a substantial amount of money, more money than you'll ever make. Okay, noted. I shan't be buying that house. All right, but if they tell you that, give you some basis of comparison, how much is that house? Well, it's not as expensive as yours. That's all I can tell you. All right, well, you still don't know, but you know that yours is more expensive, so you have some way of comparing. All right, so you have these reds and these blues. Sometimes it's, well, I have this many, and sometimes I have this many. This is more than this. I don't need to know that there's 7, right? Sometimes they just say, I have this many. They don't know that this is the number 4, but that's not important, right? Because they know that they're holding up more fingers here than they are here, right? 4 fingers versus 3 fingers, or this many fingers versus this many fingers. This is more than this, right? Problem solved, right? So very often we get bogged down with terminology. I can't remember how many times in my 8th grade math class the teacher would say, when a student would ask, how do you do this problem? The teacher would say, okay, you take 2 and you add 3. And so it's 2 add 3. That's how he'd like to say it. It's a really weird way of saying it, but that's the way he wanted to say it. All right, so 2 add 3 instead of 2 plus 3. So if he asked a student, what is the result of this calculation, and the student said 2 plus 3, he would correct the student. No, it's 2 add 3. You're like, okay, first off, you're getting a little too bogged down on the terminology here to the point where it's distracting. And secondly, you're not even right. Technically it's 2 add 3, it's 2 plus 3. It's the addition of 2 and 3. There's like a bunch of different ways to say it. Just switch over to a different language if you want, It doesn't, there's many different ways of saying the same idea. Right? Eventually, you have to get to a formal way of understanding mathematical concepts, but you don't have to start off that way. And you don't even have to get there until, and this is not an unreasonable thing, you don't even have to get to the formal mathematical way of discussing terms and ideas until the state says that you do. In that, we're talking state tests. All right. And that's really all it comes down to, because you can, if you're just going by the years, you can get all the way through middle school before you even have to learn a single proper word of mathematics. Right. So just something to keep in mind. You don't have to, and especially in the elementary school, you don't have to force the issue. They do have to be able to articulate their thinking. They do have to be able to reason. They do have to be able to justify their conclusions, but they don't have to use any particular language. And you'll see that the Common Core verbiage is and the next gen verbiage is very loosey-goosey when it comes to that. And it says explain using words, pictures, things along those lines. Numbers, words, and pictures, very stock phrase. So what words? Hey, as long as they get the idea across. Now, individual teachers very often will say, well, that's not the right answer because that didn't match the answer key, I guess. But that, you're going to run into that. So that's a different story. But don't let anybody tell you that you're wrong if you're letting students explain it in a way that makes sense to them as long as it's correct. All right. And it's an opportunity for discussion. I look at it like, if you have a class of 15 people, 20 people, 25 people, it doesn't matter, a lot of people, and you're letting them explain something any way that they want, that's a conversation. Hey, I said it this way. Is that okay? Hey, let's talk about it. All right, Johnny said it this way. Mary said it that way. Christina said it that way. Hey, do those all mean the same thing? Yeah? Well, then they're all right. You know, and everybody walks away feeling like a champ, right? Because there is the emotional component too. All right, so number 4, when you thought about the process of comparing things, you came up with different bases on which to do the comparison. For example, more of something versus less of something. In what situations do we say the opposite of more is less? And in what situations do we say the opposite of more is fewer? All right, so that becomes a language component. And then I'll read the second one. Let's think about some other opposite words that can be used to compare things. For example, we can say one branch of a tree is higher than another branch. The opposite of higher would be lower. So higher and lower are that kind of opposite words. Give 3 or 4 other examples of these pairs of opposite words that a young child could use to compare things. So the first one, in which situation or what situation do we say that the opposite of more is less? All right, so we'll start with that. All right, I'm gonna actually just write them both so I can just annotate. I guess it can involve some quotes here. All right, so and really, don't get bogged down on the terminology here so much, because forget about the fact that it's the opposite of more. It's just really what's the difference between less and fewer, right? So less, if Charlie has 3 apples, Mary has 2 apples. I'm just going to smidge this down a little. All right, so Charlie has 3 apples, Mary has 2 apples. So just a quick scenario. All right, so Charlie has more apples. All right, more apples than Mary. All right, so that's one way that we could say it, but we could also say Mary has less apples than Charlie. All right, so pretty solid relationship. It's just you have a couple of quantities. One has more than the other. It's a way of getting across the idea of greater than, less than, without getting into the terminology of it. So we're talking less apples than Charlie. All right. So we could also have phrased it as a question: who has less? Right. So let me actually jot that in there. I got caught, was intending to make the question mark and that somehow became a second S on the end of apples. It was very strange. So opposite of more is fewer, right? So when we're talking the idea of fewer, it, it's really getting at the same idea, generally speaking, right? So we're talking about less than, or can you say fewer than? You could, but we could say, and we'll stay with the same scenario. I'll just highlight that. Has fewer apples. Right, that's one way to say it. Right, but there's another one, right? And so depending on how you phrase things, we could say that Mary has one fewer apple. Well, actually, that would be a bad example because it's a singular. So that actually wouldn't make sense here. But it would if there was a difference of more than one value, so 3 fewer or something like that. It's just one fewer is just awkward phrasing. So we tend to stay away from that. But if we categorize it as an interrogative, it makes a lot more sense. But we could rephrase everything to be the same way, where it's Mary has fewer apples than Charlie. So we can make that statement. I'm just going to do a little copy paste job. All right. Now, the issue that we run into here is that I'm talking about what we call, and so without getting too crazy into the mathematical content, especially talking to very young children here, this concept here, fewer, only applies to what we call discrete values. And I'll just put a note here, countable. All right. So we could say all the same things for fewer that we said for less, unless I change the context and I say something like, Charlie has 3 pounds of apples. Mary has 2 pounds of apples. All right. Then I would need some sort of qualifier in front of the apples in order to allow for the use of fewer, because I could say Charlie has more weight. You know, his apples weigh more than Mary's. Mary's apples weigh less than Charlie's. You know, because we could get into the idea for when we're dealing with less, we can get into the idea of what we call continuous information. All right. So the non-countable things like weights and times and heights and things that are measurable. All right. So these scenarios can apply to both countable, so we know that that's discrete, and measurable information, which we call continuous, but I don't want to introduce that vocabulary term because that's just a little too much, because you would never use that term on this level. Discrete sometimes comes up. It's more for your own knowledge than the students, but it sometimes comes up on that level, right? So it's what you're using it for, ultimately. right? So this is just one example, but you can think of other things, I'm sure. But again, you want to think of things that aren't going to involve people's heights and weights and stuff along those lines, right? I mean, staying away from the concept of weight is always a solid move, you know, just just dangerous territory. Let's think about some other opposite words that can be used, compared things. Oh, sorry, I already read this. So we can get right to it. Let me go purple for those keeping score at home. All right. So we want pairs of opposite words that a young child could use to compare things. Well, you get your classic hotter and colder. Or colder and warmer if you're playing the game, you know. Wetter. Well, I'll just say wet, dry. You can vary it up any way you want, up, down. It may sound a little iffy, but stay away from left and right unless it's the purpose of your activity. All right, so left and right, and I'll put a star on that one. That's for instructional purposes only on the youngest levels, right? And that has to do with the fact, I think, hopefully it's pretty obvious that they don't all know their left from their right. And if you're basing an activity on a kid's ability to determine left and right, you're just asking for trouble, right? And then you get faster and slower. But be careful about how you quantify that. And again, preschool level, everybody wants to be friends. You know, you get a little older, you're talking about third, fourth grade, into that territory. You say you ask the students to give an example of faster and slower, and the first thing you're going to do is like Timmy and Chris. Timmy's faster, Chris is slower. You know, and it's like, oh, okay, well, Chris, I'm sure feels like $1 million now. So that kind of thing is things to be, you know, stuff to be mindful of, right? So, you know, you got the mathematical stuff, which, you know, like I write hotter, colder, wet, dry, up, down, left, right, faster, slower. You're like, where's the math? It's all the math. Because again, the elementary school teacher's job is to not screw up all the learning that happened in the 5, 6, 7 years before that student got to them. And, you know, if you do your job right, then you can build upon those foundations, even for students that, you know, like they, you know, have rough backgrounds, they have backgrounds where it's just so vastly different from the other students in class. You could always work to find the commonality between the student, one student and, you know, the rest of the population, right? So always part of the challenge, but a very rewarding part of the challenge, right? So that's that. And so what I'm going to do is kick over to the notes. We're on negative numbers. So again, if you're just kind of flipping around trying to figure out where we are, we're always working through the course content folder. So, you know, it's a good time to stop and review that. Negative numbers have a very long and storied history, right? Which you can read about on this link if you click on it. I can give you the gist of it, though. You know, and so historically, what originally was the case is that, you know, people needed to count. They needed to find value, determine the value of items that they possessed. If they were selling items, like, you know, how much money they would get for the items that they're selling and or trading or whatever. But then the concept of credits and debits came into play. And so the idea was, I mean, you just think of it this way: if you have a farm and you're planting corn, you know, if you didn't produce any corn, then you have zero corn, right? But if you were supposed to produce, I'll just make up a number that shows just how little I know about farming. If you were supposed to produce 1,000 ears of corn and you didn't produce them, you could say that you have negative 1,000 ears of corn, but probably not. You still say, what do you possess? You possess 0 ears of corn, right? Now, the context is the driving factor, because if I were to tell you that this farmer was already paid for the corn that he was supposed to produce. So this farmer was supposed to produce 1,000 ears of corn, was paid already in advance for the 1,000 ears of corn, did not produce those 1,000 ears of corn, and then spent the money. Now we got a problem, all right? So he owes not only the money back, well, he owes one of two things. He either owes the money back to the person who gave it to him, or he owes that person 1,000 ears of corn. So if that farmer goes to the individual and says, all right, I owe you 1,000 ears of corn, that individual is not going to write down, all right, 1,000 ears of corn and not label it in some capacity. He's going to put down that he is owed 1,000 ears of corn, right? So instead of writing owes or owed, the symbol, the negative symbol was created. It actually was created after parentheses. Parentheses was the first way of designating a negative number. And if you're familiar with Excel, Microsoft Excel, you'll know that when there's a negative value, the default setting is to just leave it as positive, but put it in parentheses, right? So if you owe $10,000, it would say parentheses around the $10,000, right? So the parentheses notation came out first, and then they said, okay, let's just put a dash in front of it, all right? But then they realized that the operations, mathematical operations, still applied. So if I took the negative 10,000, the quote unquote negative 10,000 or 1,000 ears of corn, and then the next year I produced, let's say, 5,000 ears of corn. Well, I owe Farmer Bill down the street, I owe him 1,000 ears of corn. So I know that I have 4,000 ears of corn to work with. How did I get that? I took the 5,000 that I just produced and I removed the 1,000 that I owe him, and that left me with what remains. And so that's where the concept of negative also being minus, being consistently the same thing, that's where it kind of entered into the history of math, right? So it's very important stuff, because math or the world as we know it doesn't exist without negative numbers. But conceptually, there's really nothing too crazy about it, because all we really have to do is just start counting the same way we would, just instead of 0 to the right, 1, 2, 3, 4, 5, we start 0 and go to the left, 1, 2, 3, 4, 5. But because we're going to the left, we slap on a negative number, all right? So those negative numbers here represent a leftward movement, right? So represents movement to the left. All right. So the reason I can make that claim is that it represents movement to the left is because the positive numbers represent movement to the right, right? So the negatives represent the opposite of positives. So the negative direction is the opposite of the positive direction. That's a very, very critically important piece of information. And it's also something that you can teach kids at a very, very young level and just rely on the elementary school teachers to not screw it up, right? So you look at it and say, all right, the only thing I ever struggle when I'm explaining stuff, sorry, time out. Remote problems here. The only thing I ever struggle with is like, well, what names I'm going to use in the examples that I give. So you have Lloyd is participating in an activity, and he's partnered with Jake, right? So Lloyd has to take 10 steps in the positive direction, all right? So they're standing right next to each other. You tell Lloyd to take 10 steps in the positive direction. The key here is you don't tell him what the positive direction is, right? So he's going to figure out that that means forward, all right? So then Jake then needs to take 10 steps in the negative direction, right? And that's where the challenge is going to come into play. So everybody's partnering together, and you give each one a different set of instructions. So some of them are moving 10 steps, some of them are moving 5 steps, some of them are moving differing values. Maybe Jake's moving in another activity, Jake's moving 5 steps in one direction, and Lloyd's moving 3 steps in the other direction. But eventually they should come across the idea that the direction of negative is based strictly on whatever the decision is as the direction of positive, right? So if Lloyd decides when he's moving 10 steps in the positive direction to sidestep to the left 10 times, then Jake should be sidestepping to the right 10 times, all right? So, but the key here is to not tell them any of this. You just tell them the instructions of, you give them a card, depending on the age group. I mean, I'm assuming that for the most part, when you start getting into negative numbers formally, you're probably not talking about preschool and kindergarten, but you could even do something like this on those levels. But you'd have to give verbal instructions for the younger ones. But you can give, let's say a second grade class, break them up into groups, and you can, groups of 2, and you can say on the index card, one name, one person A, if you want, 2 steps positive, person B, 4 steps negative, right? So, and then let them act it out. And then, give them a few minutes to rehearse. There's nothing wrong with a little bit of rehearsal. The groups can comment, they can interact with one another, so give each other feedback along the way. That's a formative way of assessing their own, self-assessment. And so when push comes to shove, they at least have, have a little idea of whether or not they're on the right path. By the time you come over and you say, okay, let's show me what you got, they should at least have given it a fair amount of thought before they just, I took 2 steps this way and 7 steps that way, or we both went this way and we don't know what the hell's going on. They're trying to figure it all out, but they're figuring it out together. All right, so very simple example, nothing too crazy, but it's also a formative way of not only assessing, but also gaining instantaneous feedback. All right. Hey, you got also the formal instruction here. We can think of negative number, negative n is the opposite of n. Now we're getting into the algebraic definitions. Negative 4 degrees Celsius is 4 degrees below 0 Celsius. Altitude is negative 50 is 50 below sea level. The key there is that there is some benchmark that has been established. When you're dealing with it strictly numerically, you're dealing with that benchmark being 0. All right. So I'll just make a note of that. Mathematically, cutoff between negative, I'll just write the word out, it's gonna look weird, and positive is 0. All right, but it's very important to understand that 0 could be wherever you want it to be. All right, where do we start? You give them the index card with the information of 10 steps forward, 2 steps back, whatever. Where do we start? Where are you? You start right there. All right, so you could have a lot of fun with this, and you can also vary it up. All right, you can designate, and this is where an activity like this can get really interesting. You can designate some sort of abstract idea as being positive. All right, so you know, if you were to say that this is a positive movement, right? So conceptualize that, just a snap of the fingers. I'm calling this a positive movement. What would be the negative? You know, and have the kids talk about that. I don't even know, you know, but you'd be surprised what they come up with. You know, so maybe they come up with a different sound. And they say, okay, well, that's a sharp, loud sound. So let's come up with a dull, quiet sound. You got the idea. It's the opposites. Perfect. You understand negatives. All right. The examples below, these are the you know, I'm going to do math examples. Each of the following number lines below has a mistake. Find the mistake and explain how you would fix it. The first thing I'm going to do is just kind of chuck in here what an ordinary correct number line ought to look like. So I'm going to call this correct number line. All right, 0 right smack in the middle. Even increments, always even increments. Whatever you want to go by is fine. You could scale it any way you want. You go by 5s, 10s, 20s, whatever, but it has to be consistent incrementing. All right, so let's say in this case, I just want to go by ones. 1, 2, 3, 4. And then I'll pop in a 5 here for good measure. Whatever I do in one direction, I have to go in the other, again, with consistent spacing. This is the part of class where I would say, if we were in person, by a show of hands, how many people have ever lost credit because, not because they didn't understand the concept in math specifically, but because they didn't use a ruler, or they missed a label or something like that, you know, and usually like everybody's hand goes up, and then all the fun stories come out about like the weird cases in which you've lost points. Instead of doing that and going around the room, because it's a little tricky in the Zoom environment, what I'm going to do is I'm going to offer you up a bonus exercise. I'll put it on Blackboard later on, and that bonus exercise is going to be to tell me the story of the weirdest way that you ever lost credit on a math assessment. All right, just so you know, I'll share those. You know, assuming I have your permission, I'll share those stories in our next class together. All right, so that'll be the way I'll handle that part of it. But you know, it's almost always something like, I didn't put the arrows, so I lost a point. I didn't do this, so I lost a point. Now, we'll talk about grading later on in the course. I'm not going to label everything here, but you get the idea. So I could just do ... I throw in the infinity. That's more for your reference, the infinity and the negative infinity, because you don't really talk about you talk about conceptually the idea of infinity pretty early on, but you don't talk about it formally until much later in their academic process. But I figured I would just at least get you the number line and show you what a correct one ought to look like. I've seen, and I honestly don't remember too much about grading when I was a student, but as I've become, I'm a teacher a long time, and I've done a variety of different grading practices, and I've noticed that some people, some teachers, just just flat out don't care. Like, grade's a grade. It's my way or the highway. There's that. Aside from those folks, the overwhelming majority of people have the most positive intentions when it comes to grading, but they don't necessarily know the math enough to come up with an equitable grading system. And so I always, for this course, I always budget some time at the end, because we talk about addition, subtraction, multiplication, and division, and a little bit of percents. There's no reason why we can't talk about different types of grading systems, right? And so you could do a point system, you could do a weighted system. We do a weighted system for your average in this course. And the benefit of that is that it guarantees that whatever I say the weights are for a particular category, that's what they're going to be. Because I have seen everything, and I've even I'm still kind of dumbfounded by it. My son comes home, and this is over the course of years, so it's in 4th grade now. Fifth grade now. So he comes home with a bunch of assessments years ago. And the assessments were like a unit test, a homework, a little exit ticket, blah, 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 right? So the teacher put everything as a percent out of 100, all right? So on the unit test with 20 questions, he got everything right, so 100. Wonderful, great job. Homework, same deal, 2 out of 2 equals 100%. Great, wonderful. In my mind, I'm like, well, that's a different 100 than the test, surely, right? Because there's no way they could be the same in terms of their value, because one's a small homework assignment, the other's a test, right? Then you have the exit ticket. So a 3 out of 4 on the exit ticket, so 75%. I'm like, well, surely that's not going to count the same as the test, right? So the long story short, the teacher took all of these assessments that were in percent form to compute his average, added them all up, and divided by the number of assessments, right? So we're talking about number lines here, and this is the most basic entry into the concept of scaling. But what that did, this approach to grading, is it took a test, a big unit test, and made it of equal value as a small exit ticket, all right? So the tick marks on the number line, every assessment was equally weighted, all right? And so, I mean, that's great. If you got a few problems wrong on the test, that actually would have been better than losing 1 point on a 4-point exit ticket, all right? So, grading becomes a really important thing, but it also has everything to do with scaling, which has its foundation in the concept of a number line. So if you yourself struggle with the concept of scaling, like creating a graph and having an appropriate scale, it goes all the way back to this concept, all right? So the benchmark is 0. We start there and we build out. We go to the right. I don't know if it's a mirror view on your end, but we go one way for the positive, we go the other way for the negative. The standard rule of thumb is the right is positive, the left is negative. If we could go forever to the right, we'd get to positive infinity. If we go forever to the left, we get to negative infinity, right? In the case of the first example, the numbers they're backwards, right? So I'm just going to use a little arrow here. These two jammies here should be switcherooskied. So that's the problem right there, right? In the case of number 2, same deal. The values are out of order. If they're going to increase in size, right? Forget about the sign. The 7.1, 7.2, it should be going the other way, right? So the 7.1 should be here, assuming that we're keeping the 7.0 where it is, and the negative 7.2 should be over here, right? Oh, it's hilarious. I accidentally put a correct one in there. Look at me. I revised this recently, and I I changed the example so that there would be one correct one, but I never changed the instructions. It was supposed to be a multiple choice kind of question, right? So, all right, well, you win some, you lose some. All right, so this one is correct. All right. So typo bonus opportunity for somebody. And again, to gain your bonus points for typos, all you have to do is send me a message on Remind saying where the mistake is and what the fix is. First one to do that gets a bonus point. So 2 out of the 3.
What's Remind?
Say again?
What's Remind?
Remind is the messaging service that we use in this class to send announcements, etc.
It's on Blackboard?
No, it's a separate app. I can fill you in on that in a little bit.
Okay, thank you.
No problem. The 3. Wrong. Okay. So I'll fix that later on at some point. All right, but that's the idea. All right, so very important that you get the ordering for the number line, but the negative values have their part to play in all of this. We have operations associated with negative values, and so those operations are addition, subtraction, multiplication, division, just like they are for positive numbers, but we have a whole set of units related to that stuff coming down the line. So, and all the pedagogy that goes along with it. All right, so I'm going to save this one and open the next one. 718. All right, so what I'm going to do here, so what I'm going to do here is I'm going to get going on this page, then we'll take a little break, and then after we come back from the break, I'll start talking to you about the assessment. Okay. So lessons 1.3, 1.4, reasoning to compare numbers in base 10. All right, so you can have a number system in base whatever you want. We have an entire numerical system that's specifically in base 10, which means that it's in a 10 number cycle, right? So the pattern is repeated after every 10 numbers, the pattern is repeated. So 1, 2, 3, 4, 5, 6, or well, 0 through 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we move up to the 10, and then we repeat the process 1, 2, 3, 4, 5, 6, 7, 8, 9, but we call them something else, 11, 12, 13, 14, 15, all the way up to 20, 21, 22, 23. So it's the same pattern, the same relationships, just in a different set, all right? The rationale behind using the base 10 system is really more than anything else convenience, right? So I'll read the blurb here. We compare numbers in the base 10 system by looking at the first place of the greatest value, then moving to places of lower value if the numbers agree in the place of the greater value. So it's basically start on the left and work to the right. On number lines, numbers become greater as one moves to the right. Given any 2 distinct numbers, there are infinitely many numbers in between. So taking the negative of 2 numbers reverses the comparison between them. So that extra little blurb there is a source of great frustration for many, many people. People, not just kids, right? Because the size relationship is reversed, and so and everything that goes along with it, right? So we have strategies for comparing these values, but you can really just kind of use what works for you, at least in the early going. But when you take into consideration all the different learning styles, you see that there's some things here that you might not have considered, right? So given any two numbers in base 10, including negative numbers, determine which is greater and put any collection of numbers in order from least to greatest or vice versa, right? So if you're comparing numbers in base 10, this first thing is really just basically saying, make a list. And then if you have more than two numbers, work with them two at a time. So that you would say, okay, if I have the numbers 1, 2, and 8, I would say, all right, which is bigger, 1 and 2? 1 or 2? I'd say 2. Okay, so 1 goes to the left of 2. All right, which is bigger, 8 or 1? All right, so 8 goes to the right. Which is bigger, 8 or 2? 8 goes to the right, so the order would be 1, 2, 8. Right, that's really the gist of what number 1 is talking about. Right. Another way is an explanation. Explain the rationale for comparing positive numbers in base 10 by first comparing the place of greatest value moving to places of lower value. That's what the initial blurb was saying. Draw rough pictures of bundled objects to show one number is greater than another. That we talked about that before, when we were going over the investigation. Sometimes you don't need to know the numbers. You just need to know, hey, this has more stuff than that, and that gets the job done. Right? Describe and draw pictures representing numbers as lengths and showing that one number is greater than another. Right? That one's a tricky one. That should, in my opinion, there's different schools of thought on this, but that should be more of a guided exercise on the part of the teacher, because if you leave it to the kids to come up with that one on their own, and you say, okay, compare 8 and 4. If they don't know the size relationship between them, that they're not going to be able to draw a picture that demonstrates the size relationship between the two values, right? So they wouldn't necessarily know to make the 8 double the length of the 4. So if you were to give them a predetermined length and say, all right, what's bigger, 3 or 2? And then show them, okay, if I want to see 3 as a length, I'm going to take this predetermined length and put it end to end with the same length, and then do that a third time. So that's what a length of 3 looks like, and then do the same thing, but only for 2. You could see, oh, this is okay. This is longer than that one. And later on in their education, you could start getting into, well, how much longer? 1 unit. Okay, well, what about in terms of a multiplier? This one is 2/3 the length of that, so this is 3/2 the length of the smaller one. So to start off with the fractional stuff would be just a disaster waiting to happen, but you can build to that sort of thing. And it goes back to the theme that I talked about, I think 2 classes ago, where you can use the same example like 10 different ways, 100 different ways, over and over again. Sometimes building that familiarity by always referring back to the same general theme or scheme, and then just building off of that gives the students some grounding and familiarity. So if your math lesson, let's say you're a first grade teacher, and you want to have, because you don't have to do math every single day on that level. I mean, it all depends on what the school district wants you to do. But, you can plan it out in a reasonable way. It just has to, you just have to fulfill the curriculum. But if you wanted to have a theme for the year, and every day, ask a new question related to that theme, just one question in the beginning of the day, that could be your math for that day, and so that could get the job done. You could also, like if you didn't want to do that every single day, you could do it once a week. You can kind of split it up. Number lines we talked about. amounts owed, I got into that earlier. Given two distinct numbers in base 10, find another number in between them. The concept of betweenness is so easy that it confuses people, right? The idea of, all right, give me a number in between 1 and 11, right? They're not going to have
7.
Right, exactly. Now give me a number between
Sorry.
a number in between 1 and 2.
1.5.
1.5. Right? Most of us go directly for the middle number, whatever's smack dab in the middle. Not many people are going to say 1.3, 1.7, something like that. The instinct is going to go right for 1.5. Most people, I mean, it's very rare that they're going to give it to you in fraction form. They're not going to say 3/2, or 4/3 or something like that. They're probably going to say, the 1.5, and that's perfectly acceptable, except for the one kid who wants to be a wise ass and say 1.000000001, or 1.999999998. And that's good too, because that shows that they know what they're talking about and they're engaged in the conversation. I think the wise asses in class get a bad rap, because if they're being a wise ass related to the content, that means that they're actually listening to you. And you already got half of the battle won, right? Now you just got to get them to be productive in the process, all right? So example here, explain in your own words why we compare numbers in the base 10 system, starting in the leftmost place, where which there is a non-zero digit, and then proceeding to the right if necessary. For example, we compare 234 and 219. So actually, let's just write that. 234 so they're both 3-digit numbers. So we could start at the 3rd digit in both cases. So we would start with the 2. So that's the same, so we move to the right. All right, so when we move to the right, we say that 3 is more than 1. So the conclusion is 234 is more, keep it in simple terms, than 219. All right, conclusion is 234 is more than 219. And so the question is, okay, so why do we start there? Why do we start at the 2 and work our way to the right? Why didn't we start on the right and work our way to the left? Right, and so there's a few different ways that you can explain it, but the idea here is, if we started on the right, we'd be looking at 9 being greater than 4, right? Which would leave us with the conclusion, because it's not the same, so we would immediately jump to the conclusion, with the conclusion that 219 is more than 234, which is not true. All right, so there's the fact that it's just not going to give you the right answer, but it doesn't really answer the question of what is it about the base 10 system that allows us to compare numbers in this way. All right, so I'm going to just kind of give myself a little bit more room here so I can stay on the screen. All right, So the base 10 system, again, it has to do with the cycles and regrouping. So we're taking 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a collection of 10. Then once we get to 10, we now have a set of 10 that's one of those 10. So that gives us the number 10. Then we gain 10 more values. So 11, 12, 13, 14, 15, 16, 17, 18, 19, right? So those values are now collected and added onto the 10 in order to get us like register. If you think of it, it's like we're leveling up to 20, all right? So once we level up to 20, we now have the first set of 10 and the second set of 10. Then we level up to 30, level up to 40. And then once we get to 100 values, we can call that number 100, gain 100 more values, we level up to 200, all right? So what happens is every place we can do this, we use the base 10 system from left to right, because each digit represents a collection of values. And I'm just gonna write big, and then I have to do it this way because of my nerve damage. It's a fun position to be in. Sarcastic. So each digit represents a collection of all values based the place of the number to the right. My Apple Pencil just died. No. I think it really did, actually. Hold on, let me just turn it off. Disconnect Apple Pencil. All right. And so what that translates to in normal people speak is that, and we have the diagrams in our notes and all that stuff, but if we look at 1,000, for example, that's a collection of 10 sets of 100. All right. 100, 10 sets of 10, and so on. So what we're actually getting from this is the idea that if you start on the right, you're accounting for everything you start on the left, you are accounting for everything to the right of that number, right, already. So there's no need to count it again unless you determine that that particular place, if it's the fourth decimal place or whatever, if it turns out it's the same. But if it's different, then you've already gotten your conclusion, because we know, like, for example, 3,000 is more than 2,000. So whether it's 3,200 or versus 2,700, the 3 is more than 2, so problem solved. That's really all it comes down to. Right? But articulating this and getting this across to a small child, and the bigger numbers you wouldn't really get into at the youngest ages, but you would eventually have to have this conversation. But you don't just give them these definitions. You don't give them the terminology. You don't use fancy language. You explain it in simple terms, and using the activities and manipulatives and things like that, you get the point across, right? So a lot of it is really more of the flavor that you bring to the class rather than just some textbook jargon. I got a kick when I was revising the curriculum to go remote. I came across somebody's notes online, and they were talking about the textbook for this class. And I don't know if any of you saw the textbook or actually even got the textbook. That thing's a monster. It's huge. And we only use like the first third of it if we were to use that textbook. It's like huge. But somebody wrote in their syllabus, some professor, that you should hang on to this textbook. You know, you'll need the textbook. We're going to be using this throughout the course. And you'll be referring back to that when you're a teacher. When you go out into the job, you're going to refer back to this textbook. And I actually laughed out loud when I saw that. You're not referring to a textbook to tell you how to teach this stuff. You're going to refer to your own experiences and, of course, Google. But you're gonna look stuff up online, but you're gonna fill it in with your own flavor, your own preferences, and you're gonna go from there. There's absolutely no way you're just gonna grab somebody's example out of a textbook and just slap it down on a piece of paper and give it to a bunch of kids without making it your own. You know, you gotta, like, that doesn't make any sense. So, you know, there's something to that. And so when you look at definitions that I give you and examples that I give you, hopefully the immediate thought is, well, and I really mean this, well, I'm not doing it that way. That's not going to work for me. That's not my personality. That's not my style, because that's how it should be. You have your own style, your own personality. You should take, you know, these concepts and tailor it, or tailor your personality, or vice versa, to make it all fit together. That's the idea. Right. So at this point, I'm going to